So thank you very much for the introduction. Thanks for the organization. Thanks to Xiong and James and all the organizers. It's 6 a.m. here, but sun is already up. So I'm going to talk about state estimation today, and essentially for robotics. Okay. So in this talk, I refer to indifferently to a filter or an observer as a state estimator of a dynamical system. So when you do well, autonomous driving or robotics, obviously state estimation is an important part of it, and you need to localize yourself. So as an example, I'm going to try well, discussing a dynamical model for the robot you see on the right. This is a robot that's driving in the corridor of École des Mines in Paris, and let's discuss a dynamical model for that, because it's the first step for state estimation. So it's usually the dynamical we use for this kind of small robots, wheeled robots, is usually referred to as the unicycle equations. So you see, you have the XY coordinates. So this is the robot viewed from above. XY encode the position of the robot, and theta its orientation. So the unicycle equations, they essentially say that when the robot is there, its velocity as the wheels roll but are assumed not to slip, its velocity is tangent to the path it's following. So that's what's encoded in those equations. Time derivative of xy is u times the vector cos theta sin theta, and theta dot is equal to omega, the angular velocity. So omega, yeah. So those quantities, u and omega, are inputs that are measured by that can be measured by wheel speed sensors. U is computed as an average of the wheel speeds, whereas omega is computed as a difference between the wheel speeds, the angular velocity. So the problem in practice is that those are imperfect inputs, and sensors are noisy, so they're not measured perfectly. So, well, to illustrate that, we could assume that we constrain the robot to roll on rails. So we know that it's going in a straight line, and then we could look at what the wheel speed sensors measure. So this is typically what we're going to obtain from the sensors. So they're wrong. It's corrupted by errors. And if we perform this experiment many times, this is the kind of thing that we obtain. We obtain a dispersion of the endpoint as a result of the noise in the sensors. So when I did this talk, well, 2 months ago, somebody said the signal to noise ratio is ridiculous. Well, this is just an illustration, right? So what I did there is that I put some Gaussian noise in the sensor reading, and I just did that experiment many times, Monte Carlo simulations, and this is what we obtain. So, well, what's the problem with that? Maybe it's not clear to everybody. If you take a linear system, so linear equations, and you add noise, Gaussian noise in the equations, then the dispersion of the state under the effect of noise is Gaussian. So this is the kind of dispersion of the endpoint that you would obtain if the system were linear. If it were linear. And this would be fine because we have many tools to accommodate Gaussian distributions in state estimation. But what the distribution that you observe on the left there is not linear. And if you think about it, it resembles a banana. This is this was noticed, early noticed in a well-known ICRA paper by Trun and co-authors when they discuss this dispersion in robotics, and they say it resembles a banana, and they come up with solutions based on particle filters to capture this dispersion. It turns out that a few years later, Greg Chirichian, along with co-authors, showed that actually this distribution that you observe on the left, the banana distribution, may be considered as Gaussian, except that you need to change coordinates. So in some alternative coordinates related to Lie groups, Lie group theory, this distribution, this banana distribution is Gaussian. And this is an insight by Greg Chirichian. So here's a few references. So the authors that coined the term banana, the one I talked about, Trun and his co-authors, they wrote a very successful book called Probabilistic Robotics. And this book is about how you handle uncertainty in robotics, and especially about using particle filters that were very fashionable at the time to capture the uncertainty. Then there's this book about using Lie groups in robotics as an alternative, and by Greg Chirichian, and this is where he explains all this theory that's related to Lie groups to capture banana distributions, and a very good recent book from Canada that you can look also into is the recent book by Tim Barfoot, especially if you want to learn about Lie groups for robotics. So this is the outline of my talk. So we've just seen an example from robotics, and now we're going to take a dive into the theory, the main theory, linear observers on group and natural applications. So we're going to do a little bit of control. So I'd like to remind you the linear case before we go to the Lie group case. So consider a linear system with state X and observation Y. So this is the dynamics. So you have a dynamical linear system. A here is an input, a non-input, and assume that you have a measurement Y. So in those equations, there's no noise. And from now on, we forget about sensor uncertainty and noise, just to explain you the theory. And then we'll get back to it by the end of the talk. So the goal of state estimation or observer design or filter design is to estimate the state X, which is unknown, from the measurements Y, which are an incomplete indication of the state, and from the dynamical model as well. So linear observers, this is how they work. They're based on a two-step process. First, you propagate the estimate. So propagation step is merely a copy of the dynamical system. And then you, at the update step, you correct the estimate of the state in the light of the measurement Y. Okay, so to do that, you compute the prediction error. So this is the discrepancy between what's actually observed and what you predict you will observe, okay, as y is h times x. You form this difference, and then you convert it through a gain matrix into a correction term that's then applied to the estimated state to nudge it towards the true state. So, yeah, I'm sorry, I've transferred my presentation. It was on PowerPoint, and I transferred it on Keynote yesterday. So there are a few bugs. So now you have a linear system on the left, and you have the linear observer on the right. Okay, and so you would like to, of course, you would like to tune the gain matrix in order for the observer to provide you with good estimation of the actual unknown state variable x. So to do that, you form the estimation error, which is the difference between the actual state and the estimated state. And this is just for analysis and gain design. And then you write what happens to this error that you would like to decrease. So at the propagation step, by looking at this, those two equations in blue and forming the difference, it's easy to see that, well, the a's disappear, and you end up with a fx minus f hat x, and this is f times the error itself. You can also look at what happens to this error at the update step, and it is easy to show that that this is the equations that's verified by the error at the update state. So what's very important about that is that, as you can see, the propagated error is a function of the error only. And in the same way, the updated error is a function of the error only. Okay, so the propagated and updated error are a function of the error that do not depend explicitly on the state. Okay, and this is entirely owed to the distributive property of linear maps. Okay, you have fx minus f hat x is equal to f times x minus hat x. This is the distributive property, and in both cases, propagation and update, this is this property that's at play. So, well, the important point about observers in the linear case is that, I mean, to me, is that the error system is autonomous, meaning that the error at propagation and update is only a function of the error before. So I call this equation autonomous in the sense that it's not dependent on x or hat x. And then once you have this error system, your goal is to design the gain matrix L here to have the error go to 0 so that your estimated state is a good approximation of the true state.
Excuse me, can I cast a question, a very quick one?
Yes, of course. Yes.
Assuming at the observer side that the AN is known, and is that a rational assumption to have?
You mean to assume that we know AN?
That's right, because I assume that the observer is something that is implemented in the controller. So you need to have an accurate measurement of AN in order to come up with what you have explained. And I'm wondering if that is a correct assumption.
Yes, yes, yes. Well, it's standard, and AN is considered so normally it's in the literature it's like B times UN. It's more U than A, but I put an A because of what's following. And so yes, it's a common assumption to assume that A is an input and it's known.
And then AN is known, then the uncertainty is known, and we don't have a problem then.
Okay, so yes, we still do have a problem. So as you said, you can assume that you know A up to some noise and uncertainty that you can then add in the process. But as I said, here we assume that A is known and there's no noise, but we still have a problem because Y here may be of very small dimension as compared to X. Okay, so for instance, X is a very large, X is a 15-dimensional state, and you measure like a 3-dimensional vector. Okay, so you only partly measure X. So you still do have a problem. And still not straightforward to find X from the Y's measurement. Okay, you don't measure it entirely. So that's the setting of observer design in the control iterator. That's okay.
Thank you very much. Yes.
And of course, it's solved in the linear case, but in the nonlinear case, even if you don't, if you assume that you know the input and you don't have uncertainty, then it's still a very complicated problem and sometimes not solvable. But yes. So here you can write how the error evolves, and then you can find an algebraic condition on the ln on the gains to ensure that this sequence E is going to 0. But this is not the topic of the talk. The important point was to show you the simplifications that occur in the linear case. So now if we go back to the nonlinear case and we go back to the unicycle equations that I've shown, this is those are the dynamics. So let's take a look at the propagation step, for instance. So those are the dynamics that govern the motion of the robot. This is a copy of the dynamics. So those are the equations of the observer at propagation step. And this is the error equation. So you see that if you compute the discrepancy between the position and its estimate and the angle theta and its estimate, then you have a problem, right? You don't have this distributive property that doesn't work anymore. Since cosine and sine are nonlinear functions. So this is obviously not a function of theta minus hat theta. Okay, so you see that in the nonlinear case, we do have a problem, even for the propagation step. And the distributive property that's helping us in the linear case is not helping anymore. And so the point of my talk is that there's a way around that, and I'm going to explain it now. So maybe so what we can do here is that we can use an embedding into matrices. Okay, so the idea is to use this matrix chi as an equivalent state variable. Okay, you see that to any state variables x, y, theta, I can associate such a matrix and vice versa. Okay, so that's an alternative state, and those matrices, they bear an interesting structure. So let me detail how they are made. So they consist of a rotation matrix of angle theta and a vector xy, which encodes the position of the robot. So it's strictly equivalent. And those matrices, they encode a rigid transformation between the frame attached to the robot and some reference walled frame. So if I multiply a vector of the frame attached to the robot by this matrix, then I obtain its coordinate in the reference frame, in the world frame. So I've moved from x, y, theta variables to rigid transformations, the transformation that maps the robot frame to the world frame. So what's interesting about those matrices, the structure they bear, is that they bear a group structure. So you obviously see that if you combine two such matrices, so if you consider K2 times K1, then by first applying a K1 rigid transformation to the robot, and then a K2 rigid transformation to the robot, amounts to applying K2 times K1, the equivalent one-step rigid transformation to the robot. So the product of two such matrices is another matrix which has the same form. And in the same way, if you consider the rigid transformation that maps the frame attached to the robot to the world frame, then it admits an inverse transformation that maps the world frame to the robot frame. Okay, and this is exactly the inverse of this matrix. And this stability by composition, multiplication, if you want, and inversion defines what we call a group structure. So now that if you do that, you have an alternative way of representing state variables that bears a group structure. And this is a motivation to replace standard addition by multiplication on the state space once it's been embedded in a matrix group. So this is the slide that's coming is arguably the most important slide of this part of the talk about the theory. We're going to define what we call linear systems and observers on groups. And so now we could ask ourselves, what is a linear system on a matrix group? And to define it, we can replace the standard addition in vector spaces with matrix product. As we know that the product of two such matrices is another matrix of the same form, so it corresponds to another element of the state space. So here, if I do that, I replace plus by matrix multiplication. This is what I get in the realm of the chi matrices. I get something, okay, so this is an analog to f times x. I'm going to discuss it just afterwards, times the input. A now is just an input matrix, okay. So this is the dynamics. Then what is the property that I have used regarding linear maps? It is the distributive property. So if I seek its counterpart in terms of matrix multiplication, this is what I get. I get that by replacing the plus by just matrix multiplication, I get that phi here, which is the counterpart of fx, should verify this relation. And a map that verifies this relation is called a morphism in group theory. And now, to analyze the observer, I should use a state error. So I need to find the counterpart of x minus hat x. And in the terms of matrix multiplication, this is just multiplying by the inverse, right? So this is the error eta now that I use to measure the error between the true state and the estimate once I have embedded the state into a matrix group. So yeah, this kind of dynamics where phi here is a morphism is called group affine, and it defines well what we called a linear system on a group. So now if you consider the observer, it's just a copy of the dynamics, and let us study what happens to the state error. Okay, so this is quite easy because all those guys are matrices now. So at propagation, I multiply the propagated state by the inverse of the propagated estimate. So this is what I get. I see that the A's disappear, the input. So this is what I get. Now it's easy to show that when you have a morphism phi, the phi of the inverse is the inverse of phi, owing to the morphism property. And then by using the morphism property, I get that phi of chi times phi of hat chi minus 1 is phi of the product. And this is the distributive property in terms of group multiplication. And you see that here again, the error is autonomous. So the propagated error is phi of the error before propagation. So we have something that occurs, which is very similar to linear systems. And in fact, linear systems and groups, they generalize linear systems. So now this is what we call a linear observer on a group. It consists of a propagation step, and then which is just a copy of the dynamics, and then an update step. And I don't have time to explain the details regarding the output Y and how you do the update, but we can discuss that later if you're interested. So this is what we get, and the error evolution. So it turns out that at the update step 2, owing to the way we construct the observer, we also have a distributive property that's at play, and we get an error evolution for this kind of observer that we called a linear observer on group. We get an error evolution that's completely autonomous as well. So here, just a small point, because it's a question that I got also. So now L is not a matrix, right? L is a function of this guy, and Y is the output. So I don't really have time to explain the form of the output that we need, but Y is a vector now. And we multiply it by the matrix, so we get a vector, and then we apply some function to this vector, which maps this vector into the matrix group. And then L of this guy is a matrix that I multiply by chi. So I use matrix multiplication as well to nudge the estimate towards the true state. And I get an error after update, which is a function of the error before update only, and which does not depend on the state at chi. So once you have this error system, well, exactly as in the linear case, your goal is to design the function L here. It's a function, it's not a matrix anymore. I mean, it's a function that's matrix valued, but to have the error go to 0. So here, as eta is the difference in the sense of group of multiplication, you want eta to go to identity, because when chi is equal to hat chi, then eta is equal to identity. So what is the virtue of this autonomous error evolution property? So there are two main properties I'd like to mention. The first one is as follows. What you can do then is assume the error to be small, and then linearize the error system around the identity matrix that correspond to a null error, as the error is defined that way. If you do that, you see that the Jacobian of this map and the Jacobian of this map there are state trajectory independent, because you linearize those maps always at the same point, which is the identity. Eta is equal to identity. So you end up with two Jacobians here that are state that do not depend on the state. So this is in contrast with the EKF external Kalman filter methodology. So to remind you what the EKF methodology is, the idea of the external Kalman filter is to linearize the error system in the vector case about the estimate, and then you compute the gain and you correct the estimate through this gain. What we call the invariant EKF is a linear observer on group, so it bears the same structure as the observer I have shown, and to tune the gain L, the L function, we linearize the error system about the identity, assuming that the error is small, and then we compute the gain using this linearized system, and we correct the estimate using this gain. So although the structure is very similar, a fundamental difference arises, as here you see that you have here the gain does depend on the estimate, because the system is linearized about the estimate. And so you can have a positive feedback here that may be harmful, because if the estimate is wrong, then the gain is going to be wrong, and the correction is going to be wrong, and it can make the estimate even more wrong, right? Whereas in the invariant EKF case, you linearize always about the same point, the identity. So whether the error is very large or whether it's small, then you have the gain isn't changed. So what's the virtue of this property? So in a very beautiful paper and seminal paper, Song and Grisel, they showed that the conventional external Kalman filter possesses some convergence properties as an observer, so when noise is turned off. But there's a problem with the assumptions. You have to assume that the error is well behaved in order for the result to apply. So it's a chicken and egg problem. If the error is well behaved, then it goes to zero. But actually, it's uncheckable in practice. And as a matter of fact, the EKF may diverge in practice. So we have examples where noise is turned off and the EKF diverges even for very small errors. So it's logical that we cannot prove a convergence of the EKF under reasonable assumptions, because it does not converge necessarily. And for the group case, using among other property, using the state trajectory independence of the Jacobians, we were able to prove that the invariant EKF for the class of systems that I have shown, the linear observed systems on groups, which is of course less general, we could prove that the invariant EKF is a convergent observer. So if the initial error is sufficiently small, then it goes to zero. And we don't have to assume anything about the behavior of the error to prove that. The only assumption we need is observability assumptions of the linear case. So now there's one last property I'd like to mention of those systems. So if we look at the error propagation here, so it's very simple. Phi is a morphism, and owing to the fact that phi is a morphism, there's an intriguing property of this dynamical system that governs the error, which is as follows. So when you consider a matrix group, it comes with maps called the exponential map and the logarithm. And the log maps matrices of the group, so eta here, to a vector space. Okay, so you can associate, and it's locally bijective. So you can associate to any matrix sufficiently close to identity a vector here through what we call the log or the exponential coordinates. And then it turns out that the fact that phi is a morphism ensures that necessarily in the log coordinates, it's a linear map. Okay, so log of phi is just some matrix J times this vector. So, well, if you use this property, you realize that if the error is Gaussian in the log coordinates initially, and then you propagate it through the error system, then it will remain Gaussian, exactly Gaussian in the log coordinates, since in the log coordinates, the phi is a linear map. Okay, so this is so using this property, we can come back to banana distributions, and we show using that banana distributions, which are actually distributions that are Gaussian in log coordinates, remain Gaussian in log coordinates through propagation. So this banana property that we observed for the robot, for the small robot, actually carries over to a very large class of systems, and eventually that may be much more complicated, and with the state space being much bigger than the state space of the robot, and you still have this property that well, using those coordinates allow you to capture the actual dispersion. So this is illustrated by an experiment conducted by a group at University of Michigan. So they had this bipedal robot called Cassie, walk for 8 meters. It's equipped with an inertial measurement unit. And so they compared the dispersion of the position. Okay, so now the dynamics are more complex than those of the wheel robot. The state is of much higher dimension. It's a 15-dimensional state space. And you see that in terms of position, the actual dispersion that you observe is also banana-shaped. If you use an invariant EKF, which makes the assumption that the state is Gaussian in the log coordinates, then you capture very closely the actual dispersion of the state over many experiments. Whereas if you use conventional EKF that's based on ellipsoids, then you see that you have something which is, so it's based on the assumption that the Gaussian assumption in the original coordinates and not in the log coordinates. And so you get something which is very different from the actual dispersion of the state space. So I can show you this experiment. It's a video that you can find on YouTube that Jesse Grissel sent me. So you see, this is the robot Cassie. It's equipped with an invariant EKF. And what it does, the robot there, it's not SLAM, it's not simultaneous localization mapping. It's just it's just localization. And you see that by using this invariant EKF, it is able to reconstruct its environment, so to locate what it observes with its sensors in a 3D map, and very accurately. So this is the kind of result that you get using invariant EKF. So to finish, I'd like to show you some further applications. So, well, the prototype for the things that I've shown and estimation using Lie groups is attitude estimation. So It's a problem that has been well researched. So the idea is just to be able to find the orientation of the body. And it was a very important problem when small aerial vehicles appeared in the mid 2000s, because of course to control a drone, you need to be able to stabilize its attitude, its orientation. So those observers on Lie groups were an enabling technology at the beginning of small aerial vehicles, and especially the nonlinear complementary filter. Okay, thanks for 12 minutes. Okay, so just so it can be cast into this attitude estimation problem can be cast into the framework that I have shown by letting chi be merely the matrix, rotation matrix that encodes the attitude of the drone. Okay, so it's been well researched. There has been many works about that and exploiting the Lie group structure and coming up with convergence properties. It should also be reminded that there has been work also that had been work on using Lie groups for control, but not much for state estimation at the beginning of the 2000s. A more complicated problem is inertial navigation. So the idea there is to use inertial sensors to estimate the orientation and also position and velocity of a flying vehicle or a submarine. And it is by using the Lie group SE23 that by introducing this Lie group and the associated morphism that we could cast the inertial navigation equations into the framework that I have shown. And following up, okay, so this is the matrix embedding that you should use for inertial navigation. And following up this approach, Wang and Taibbi, Anderson, Zamani, and Mahoney and Trump also got some very nice convergence results recently. So yes, this is Axel Barraud. Most of the entire theory that I have shown have been developed jointly with him, and it's recapped in this annual review paper that's tutorial. And so this is, we worked with the company Safran, which is well, #1 in Europe for inertial navigation systems. And we could compare on flight data the difference by using an invariant EKF and a conventional EKF. So those are error, heading error for inertial navigation systems using an invariant EKF. So you see that if you start with a 5 degrees error on the heading of the airplane, then the conventional EKF and the invariant EKF behave exactly the same. So for small errors, they're strictly equivalent. But if you move to larger errors, so 30, 60, and 90 degrees, you see that the behavior of the invariant EKF is almost unchanged as compared to small errors, whereas the estimation of the EKF much degrades. And it takes it a much longer time to find the attitude, actually the heading error, the heading of the airplane. So this is quite spectacular because the difference between both, since conventional EKF has been, a standard in the aeronautics industry for 50 years, and so this motivated the development of an industrial product. So this is the Euroflir 410. It's a gyro-stabilized ball So the idea of this product was released in 2018 by the company Safran, and what it does is it's a vision system for tactical drones. It also equips it also equips well, it's also used for search and rescue, wildfire surveillance. It also equips the police helicopters, and of course for defense purposes. So it's equipped with a telescope, and it stabilizes the vision at a 10-kilometer distance. And it of course it comes with its own localization system, and thanks to that, thanks to finding the position and the orientation of the ball very accurately, you can geolocalize what you observe 10 kilometers away. And so we use this. So we use it's an invariant EKF that's embedded in this product. And the idea is that when you have initially very large initial errors, because for instance, to transport the drone in a truck, and when you switch on the system, or when it needs to be switched on to restarted in flight, then you have no idea of what your heading is, and they use an invariant EKF due to its convergence properties. They use an invariant EKF to find the heading. Okay, so I believe that I should stop now and leave the floor to questions. I had one more application I wanted to show you, but I won't have time. It's okay. Let me just skip that and move to the conclusion. So yes, basically a new field has opened up, which is, well, using these linear systems on group theory to do state estimation. And there are many things to be done now. So you could, well, further exploit the state independence of the Jacobian to the trajectory. So James is well represented in this item, as you can see, and his group. So I believe that some of his collaborators are mentioned there, and maybe there in the audience. Of course, more convergence properties. So you use those to derive theoretical convergence properties of observers. Of course, new matrix embeddings, because, well, as you have realized, well, the part of the job is to find the right matrix embedding that makes the original equations a linear system on group. Okay. Of course, the fusion with vision is an important problem in robotics, and so on. And why not apply this to control? So there's a very nice article by James and co-authors in 2020, where they used SC23, so the matrix embedding for inertial navigation to control, and the results are very interesting, and maybe we should pursue also in this direction. And of course, to finish, I'd like to thank all the people that have participated in the theory that I've shown. Thank you.